Now I'd like to speak about the transmit pulse. This is the pulse of ultrasound energy which the machine sends into the body, where it interacts with the tissues, creating echoes, which then create the ultrasound image and other information. What do we mean by an ultrasound pulse? We mean a very short package of ultrasound energy, typically just a few cycles long. In current ultrasound machines, the transmit pulse is around 3 cycles in length. A pulse is defined in contrast with what we call continuous wave ultrasound, which is where the ultrasound goes on indefinitely. This is used in diagnostic ultrasound as well, but only in continuous wave Doppler. All other diagnostic modes of ultrasound use pulses. Now, since the pulse is about 3 cycles long, this means that its time duration is around 3 times the period of the ultrasound wave. And as I show here, this means that it can be calculated as simply 3 divided by the ultrasound frequency. For example, if the frequency is 3 MHz, the pulse duration, which I've shown on the right-hand side of the slide, would be 1 microsecond. If we were using 6 MHz ultrasound, the duration would be half a microsecond. There's another term I should introduce here, which is spatial pulse length. This is the physical distance occupied in the tissues by the pulse, and it is going to be approximately 3 times the wavelength, since the wavelength is the physical length of a single cycle. And so you can see that we can easily calculate both the time duration and the physical spatial pulse length from the frequency that we're using. Notice that with both of these measures of the size of the pulse gets shorter as the frequency increases. So as the frequency increases, the pulse duration gets smaller, and also the wavelength gets smaller, and therefore the spatial pulse length also gets smaller. This is important because the pulse duration determines the depth resolution, or axial resolution as it's called, of the ultrasound image. So higher frequency means shorter pulse, better image resolution. This animation shows you a transducer on the skin surface transmitting a pulse of ultrasound into the body. It's shown as an oval because the physical width of the pulse is generally significantly greater than its depth. This has implications for accuracy and the resolution of the image, which we'll talk about later. So this pulse travels at a constant speed through the tissue, hits the tissue interface, and an echo returns to the probe. The remaining energy travels into deeper tissues where it can interact with them. This is obviously a simple diagram with only a single reflector, and I have very conveniently made it perpendicular to the beam so the echo does return to the probe. A couple of things I'd like to point out. First, the machine can determine how deep that reflector is by looking at the time at which the echo comes back to the probe. So the machine calculates the time difference between when it transmitted a pulse and when the echo returns. That allows it to calculate the depth of the reflector. Secondly, you can probably guess that the extent of the pulse in depth is going to affect just how accurately the machine can make that calculation. If the pulse is very small, that's going to allow the machine to more precisely calculate the depth from which the scatter is coming. Here's how the machine calculates the depth from which a given echo comes. If the echo is coming from a depth d, then the transmit pulse will travel this amount of distance, and the returning echo will travel also that same amount of distance. So the total round path distance travelled by the ultrasound to create this particular echo is 2 times the depth. This means that from the time when the machine transmitted to the time when the echo returns can be simply calculated as distance travelled divided by speed. And so we have the echo arrival time following the transmit pulse is simply 2 times the depth divided by the propagation speed in tissue. The machine uses this to calculate depth from echo arrival time. So it uses a rearranged form of the equation, which I've shown at the bottom here, which says that the depth from which an echo comes is simply propagation speed times the echo arrival time divided by 2. Of course, the machine has to know the propagation speed to make this calculation, and there is an international agreement that machines all assume a propagation speed of 1540 meters per second. So this is how the machine calculates the depth that each echo comes from. The actual process of creating an image is described here. The machine transmits a pulse. That pulse then travels down an ultrasound beam, interacting with the tissues, creating echoes. The machine waits until all of the echoes have returned. So it waits until there are no more detectable echoes, and it has then acquired the information for one line in the image, sometimes known as a line of sight in the image. So that gives us one line of echo information in our image. Once all of the echoes have returned and there are no more detectable echoes, the machine moves the beam to a new position. It then repeats this process of transmitting and receiving echoes. And so it does this repeatedly with a beam in a different position each time until the beam has traversed the entire image area and created a single image. As a generalization, most ultrasound images contain somewhere between 100 and 200 lines. And so with this simple imaging process that I've just described, the machine is going to require 100 to 200 transmit pulses in total to create a single image. Obviously, this takes a finite amount of time, and the amount of time that it takes is going to depend on the pulse repetition frequency, which is the number of transmit pulses each second. So the machine can produce a certain number of pulses per second. It takes a certain number of pulses to create the image, and therefore this pulse repetition frequency, or PRF as we call it, is an important determinant of how many images the machine can create per second. Let's now look at the frame rate, which is the number of images per second that the machine produces. We need to take into account the penetration depth, P. I introduced this before. This is the maximum depth from which detectable echoes return. So that tells us that the minimum amount of time the machine has to wait between one transmit pulse and the next is 2 times the penetration depth divided by C. So this allows us to calculate the minimum amount of time between one transmit pulse and the next. The machine, in practice, estimates what the penetration depth is, and it then weights the estimated amount of time between one transmit pulse and the next. So it aims to make as many transmit pulses per second as possible, consistent with the penetration depth that it is estimating. So let's suppose that it takes a total of n pulses to make each image. Then the shortest possible time that the machine will take to make an image is 2 times n times the depth of penetration divided by C. That's the time it takes to make one image. So the number of images in 1 second is simply 1 second divided by this amount of time, which basically inverts this particular number. And so we see that the frame rate is propagation speed divided by 2 times P times N. It's common to rearrange this equation to write it in the form I'm showing at the bottom, which is that the frame rate multiplied by the penetration depth multiplied by the number of pulses per image is equal to C over 2. So what we have is that this product of 3 different machine parameters is constrained to be equal to the propagation speed divided by 2, which is of course a fixed amount. Now the depth of penetration in any given clinical application is dictated by that application. If you're scanning the thyroid gland, obviously the penetration is small and the frame rate can be high. If, however, you're doing a third trimester pregnancy scan or a deep abdominal scan, the penetration depth will need to be far greater, and this is going to cause the frame rate to be relatively low. Looking at this equation, we see that in practice, if we're not happy with the frame rate that we're getting, the one lever that we have, the one thing we can vary, is n, the number of pulses it takes to make each image. How can we change n? Well, one of the simplest ways is to narrow down the width of the image. So we reduce what's called the field of view. We make the image narrower, and this means there are less lines within that image, and therefore it can be created more quickly, so there will be more frames per second. This is very commonly done in echocardiography to increase the frame rate. Another way to achieve it is to use the zoom function while you're scanning. So you select a small area of the tissues and zoom in on that, which means the machine's only scanning that limited anatomy, which it can do quickly, and so the frame rate can be much higher. Various additional modes will slow down the machine, so things like color Doppler, harmonic imaging, compound imaging, multiple focus, all of these things slow down the frame rate. And so the frame rate is quite an important consideration. Let's just quickly run through an example. Suppose that we are doing an abdominal scan with a penetration depth of 25 centimeters, and there will be 200 lines in each image. This parameter is set by the manufacturers, the way they design the machine. Then, using the formula in the previous slide, I can calculate that the maximum possible frame rate is a little over 15 images per second. Now, this is a barely adequate frame rate for many applications. If I'm sweeping the probe quickly through the tissues, or if the tissues are moving significantly, then we're going to get blurring. So I may well want to increase the frame rate. And as I've mentioned already, the simplest way to do that is to decrease the number of lines in the image, for example, by narrowing the image down. There is another trick, however, that many manufacturers have adopted in recent years, and this is to design the machine so that it produces several beams at the same time. Typically, the number would be 4. So the machine can produce 4 beams simultaneously, which means, of course, that it is gathering the echo information 4 times as quickly, and therefore the frame rate will be increased by a factor of 4. So to summarize, I've discussed the ultrasound pulse, and that the best resolution is achieved when the pulse is short. So when the pulse duration is short, and when the spatial pulse length in the tissues is short. And this is achieved by using the highest possible frequency. I've shown how the machine calculates the depth from which each echo comes. I've then discussed the fact that the machine has to wait until all detectable echoes have come back from each transmit pulse before it generates the next transmit pulse. And this limits the pulse repetition frequency and the frame rate. The limit is particularly severe when we're scanning deep, because then the frame rate is relatively low.